Okay. My name is Yuyang Jin from Tsinghua University, and my mentor is Professor Zhai. And it's my pleasure to present our work on this launch meeting. My research interests are performance analysis and performance optimization. This work is ScalAna automating scaling loss detection with graph analysis. In this work, we collaborate with Professor Hofer from ETH and Professor Liu from NCSU. Now, let me introduce our work. A decade after Dennard scaling ended and the clock frequencies have stalled, increasing core count remains the only option to boost the computing power. Top-ranked supercomputers already contains millions of processor cores. This unprecedented growth in the last years shifted the complexity to performance optimization of parallel programs, for which scalability is a main concern now. And some parallel programs cannot efficiently use modern supercomputers. For example, this graph shows the scalability of IS in MPB benchmark on the Tianhe-2 system. The horizontal axis is the number of processes, and the vertical axis is the execution time. We find that the execution time of IS doesn't decrease after 256 processes. That is what we call poor scalability. And why the scalability is poor? It is caused by scalability bottlenecks, such as lock contention, serial code, network congestion, load imbalance, and many more. So how to improve scalability? We need first to identify these scalability bottlenecks and then optimize them. Actually, it is not easy to identify these scalability bottlenecks. We find that scalability bottlenecks may propagate to other processes through complex dependence in the program. For example, this is the main loop of CG in MPB benchmark. During each iteration, it performs a global synchronization through 3 point-to-point communications. And this figure shows its communication pattern on 8 processes. We further added data and control flow edges in this figure. Now, if a scalability bug exists in A4, it will cause a waiting event in A5 through the first point-to-point communication. Then B5 will be delayed, and then the scalability bugs will propagate to other processes. And finally, it forms a propagation path. There are many similar propagation passes when the program is running. And it causes many scalability bugs in different code snips and in different processes. The complex dependence makes diagnose even harder. So how to identify the root causes, the A4 here? This question is the target problem of this work. And currently, there are mainly 3 kinds of approaches. First, profiling-based approaches, such as HPC Toolkit, MPIP, RMAP. They use sampling techniques to profile performance data. So these approaches are lightweight. But sampling misses some important information at runtime, like data and communication dependence. So they need expertise to identify root causes, and they are not very accurate in some cases. Second, chasing-based approaches, such as ScalAna, Vampire. They record all event chases at runtime. Thus, the detection would be very accurate, but the huge chases incurs expensive costs. The last one is modeling-based approaches, such as Catwork, Extra P. They are very lightweight and accurate, but building a model needs significant human efforts and expert skills. So we propose ScalAna, a lightweight, accurate, automatic tool for scaling loss detection. There are two core ideas in ScalAna. The first one is that we leverage static analysis to extract program structure and then build a graph. Besides, static analysis can reduce runtime overhead. The second one is that we leverage graph analysis to detect a scaling loss. We propose a backtracking root cause algorithm based on the graph. This makes ScalAna an automatic and accurate tool. This is the workflow of ScalAna. It consists of two modules, graph generation and the scaling loss detection. In graph generation, there are two steps, static analysis and sampling-based profiling. First, static analysis build a program structure graph based on source code. Then sampling-based profiling collect performance data and build a program performance graph. Finally, in scaling loss detection, root causes are identified with graph analysis. First, let's introduce the first step, static analysis. We first extract control structures at compile time and build a program structure graph, and then graph contraction preserves important vertices. At compile time, InterProcedural Analysis extracts structure from control flow graph for each function. This is an example. We extract control structure and build structure graphs for function main and function full. Each vertex has its corresponding control structure in the example code. Then, in InterProcedural Analysis, we merge these structure graphs by function call graph. For example, function main calls function full, so we replace the call vertex with structure graph of function full. This is the generated graph after InterProcedural Analysis. Finally, graph contraction. We preserve communication and computation features in this graph. To preserve computation features, we set max loop depths for nested loops to keep graph concise. We also merge vertices that have little workload. To preserve communication features, we keep all communication called vertices. Finally, a program structure graph is built. Then, the sampling-based profiling module. In this module, we first use sampling-based approaches to collect performance data, including PMU data and communication data, then embedded the data in the program structure graph and form a program performance graph. We use sampling techniques to profile PMU data for each vertex. For example, this is an execution timeline. Different colors represent different code snippets in the program. The core idea of sampling is to interrupt the program at regular clock cycles and record program snapshots. For each code snippets and each processes, we collect PMU data in this way. Then we use sampling-based instrumentation to collect communication data. For example, this is an original code for MPI function, and it is invoked by 1,000 times at runtime. Now, instrumentation inserts recording code in the MPI function to record data. Every time MPI function is invoked, the inserted code will be executed. So it records for 1,000 times in total. The core idea of sampling-based instrumentation is that only under a certain probability will communication data recorded. Here we use random number generation to realize it. It is only recorded for about 10 times in total. Sampling-based instrumentation reduces both time and storage costs. Finally, we associate profiling data to the corresponding vertex in the PSG. PSG is program structure graph through call stacks. The profiling data include the PMU data, communication data, and call stacks. We use call stacks to identify the corresponding vertex in the PSG, like this. The main function and the full function and the MPI send. And then we write the performance data, PMU data, and the communication data to this vertex. Sorry. And for each processes, we embed the performance data to the PSG. And after data embedding is done for all processes, we finally build a program performance graph like this. We first build a graph for one process, and then we build and we finally build performance graph for each processes, and finally the program performance graph is built like this. We call it PPG. And now we have built the program performance graph. In the last module, we detect scaling loss, and based on this graph, and we first detect and mark some problematic vertices in the PPG, and then identify the root causes by backtracking algorithm. So first, we mark the problematic vertices. What are the problematic vertices? There are two kinds of problematic vertices. One is non-scalable vertex. It means its corresponding code snippets has poor scalability. For example, in this graph, the horizontal axis of this graph is the number of process, and the vertical axis is the execution time. Lines in different colors stand for different code snippets. We find that the scalability of red lines is much poorer than others. We mark it as non-scalable vertex. The second one is abnormal vertex. It stands for the vertex with imbalanced performance among processes. For example, in this graph, the horizontal axis is process ID, and the vertical axis is execution time. We find that the red points have significant different performance from other black points. So we mark them as abnormal vertices. Then we use backtracking root cause detection to identify the root cause. And this is the main idea, the core idea in this work. We first perform backward traversal on the PPG through intra-process data and intra-process data and control dependence, and inter-process communication dependence. In this graph, each row stands for same code snippets, and each column stands for same process. The red vertices stands for the marked problematic vertex in the last steps. In the last step, we first connect problematic vertices with backtracking paths. Starting from the last problematic vertices on the PPG, we traverse backward through inter-process communication edges and the intra-procedural data control edges. Then a path is formed. We detect many paths in the PPG in this way. Then we identify the root cause in the paths. All backtracking paths point to this problematic vertex, so we mark it as the root cause. Please see more details of backtracking algorithm in the paper. Also, we design a GUI for our tour. The upper part shows path of root causes. The lower part shows the corresponding code snippets of root causes. And the experiments are done on 10/2 supercomputer system. Each computing node has 24 cores and 64 GB memory. We also use a local cluster for some experiments. We evaluate our tool with 8 programs in MPB benchmark and 3 real-world applications. The largest scale is up to 2,000 of processes. We also compare our tool with state-of-the-art tools, ScalAna and HPC Toolkit. First, let's see the runtime overhead of ScalAna. We compare our tool with ScalAna and HPC Toolkit. This is the runtime overhead, and this is the storage costs. The blue bars are the costs of ScalAna, and the orange bars are the costs of HPC Toolkit, and the gray bars are the costs of our tool. Our tool incurs lower runtime overhead and storage costs. And here we take Zeus MP as an example to show how our tool works. First, we build a program performance graph for Zeus MP on 128 processes. Then we detect and mark problematic vertices on the PPG. Then we perform backtracking algorithm. We start from the last problematic vertices, and here is MPIR reduce, and transfers backward through data control and communication edges. Finally, we identify that the root cause is a loop in this file. We optimize this loop and significantly improve the scalability. We also evaluate our tool on other applications in the same way. We build a program performance graph and then identify the root causes on the PPG and then manually optimize them. Both performance of scalability are improved for these real-world applications. In conclusion, we have 2 core ideas in this work. The first one is that static analysis can reduce runtime overhead. The second one is graph analysis can help performance analysis, especially for complex and large-scale applications. And ScalAna is a lightweight, automatic, and accurate tool for scaling loss detection, and it is based on LLVM. In the future work, we consider redesign ScalAna based on binary, but not source code, because source code is not provided in some cases, and we try to add a weight on the edges to analyze severity of root causes. And here is some future work. It's not a part of ScalAna. we find that there exists many end-to-end systems or tools for detecting scaling loss, performance bottlenecks, or network congestion. We want to design a performance analysis framework with these two concepts, static analysis and graph analysis. So in this framework, the first module is performance data collection module. We use hybrid static and dynamic analysis in this module. And then the second module is offline performance analysis module. We want to use graph analysis to improve this module, and these two graph is these graphs is the PPG mentioned in the paper and in some real world applications. And thank you. Thanks for your listening.